Hello everybody, welcome to class. Today we're going to be talking about 3D figures. We're going to do a little activity at the end, but I want to introduce you to different types of 3D figures that we're going to be dealing with. The main one we're going to focus on is polyhedrons, and that is solids made out of flat surfaces. Now we have a couple different types here. We have the prisms, two parallel congruent bases. We name these prisms by the shape of the base, right? So if you notice underneath here, we have two bases that are triangles, so we call these a triangular prism. We have a rectangular and a square prism. Underneath here, we have a pentagonal and a hexagonal prism. So we name these prisms by the two different bases that they have. All right, and one of the other big pieces here is that all of the lateral faces of a prism are going to be rectangles. Let's move over to pyramids here. We have pyramids are pretty similar, but they only have one base instead of two, and they lead up to a point for that second part. And what that means for the sides is that they're not rectangles, but they're actually triangular sides now. So the official definition: have a polygon base and triangular sides that connect at one vertex. So how we name these pyramids, same the way that we do with the prisms. We name these pyramids by the shape of the base. So we have a bunch of different examples here. I want to show you that we have non-polyhedrons, and these are solids made out of at least one curved surface, right? So cylinder is involved in a non-polyhedron. We're going to have here, the reason I'm showing you these is because the activity we're going to do today with the Play-Doh, you will have options to actually use non-polyhedrons as well. But let's talk about the polyhedrons again. We have three different aspects of these shapes that we're trying to identify them with. We have the faces, which are any of the flat surfaces on the solid, whether it's the sides or the bases. We have the edges, which are the lines that connect these two sides. Then we have the vertices, and the vertices are the points where two or more edges meet. Okay, and we want to be able to count how many faces, edges, and vertices each shape has, because it's going to help us in determining a lot of different parts of that. Now, if we're to move on here, we have a net, which is a two-dimensional pattern that can be folded to form a three-dimensional solid. And we can actually do the same thing the opposite way, right? We can take a three-dimensional solid, we can sort of unfold this into a two-dimensional pattern. Either way works as well. Okay, so if we have this one here, we have the top, the bottom, and the four sides. The idea is that it has to remain one piece that we can fold into different ways to become that three-dimensional solid. So anytime we're given a 3D solid, we want to be able to think about what would it look like if we were to have to unfold it, and sometimes we're even going to have to make a sketch about that. So definitely something to keep in mind. Now, for a cube, we have these 6 different squares that all form together if we were to fold this up to become a cube. But then if we look at the cylinder, we have 2 circles, which are the bases. And something interesting about this is that the whole side piece of this cylinder actually can be unfolded into a rectangle, right? And that's something interesting about looking at the nets of that specific non-polyhedron, is that the net actually becomes a quadrilateral for the side. All right, same idea for the cone. We have these different parts. And we can take a look here. Triangular prism. I would say the prisms are a little bit easier just because you can clearly tell which ones are the bases. And then you have the 3 different sides that will connect them. And remember, the triangular prism, it has rectangular sides. And if we go over to the triangular pyramid, we have a base. We'll call the base the middle one. And then we have these 3 other triangles that we fold up. And when they meet at the top, they do connect at a point. Now let's talk about real life situations that we're going to see cross sections in any point in our lives, right? If we look at a tree, if we cut a tree down to determine its age, We want to see all of these different rings. Now here's the thing with the cross section. A cross section is a two-dimensional figure. It is a two-dimensional shape that is the result of cutting a three-dimensional shape in a specific way. We have many different options on how we can cut these three-dimensional figures, and they're actually going to give us different shapes for the cross sections depending on what way we decide to cut them. Okay? Now, a real definition: a shape formed by the intersection of a plane and a geometric solid. The way I like to think about this, it's a little simpler if we think of that plane here, this little piece, as maybe a piece of paper or something that we could slide into the shape itself. And the result of this paper, sort of like putting that paper into the shape, snapping a pick, and then pulling it back out. And whatever's left on the paper is the cross section that was formed from the cut that you chose. So in this case, if we cut it horizontally, we notice that the cross section comes out as a square. I want you to think, if we were to cut this vertically, maybe something else would show up. All right, and if we look over here at the cylinder, same idea. If we cut it horizontally, right through the middle, we'd get a circle. And actually, if we cut it from top to bottom, if we cut it vertically like this, we would say we would get an actual rectangle out of that cross section. Interesting stuff, something we're going to be able to look at a little better and more in depth with the visual representation of the Play-Doh that we're going to use today. Here are some different parts that actually came out of an app that we're going to use today on the iPad today or tomorrow called iCross. Gives you any shape that you want. You can cut the shape however you would like, and you can tell when these parts split open, you can see what resulting cross-section would come from the cut that you chose. So that's another way we're going to take a look at what we're doing. All right, now here's the idea. We are going to be using Play-Doh, but before we actually use it and I create these shapes, whichever shapes you would like, I want you to predict whatever shape you decide. I want you to predict, if I were to slice that vertically at any point, if I were to slice that vertically through the shape, what type of figure would result as the cross section of that 3D figure? Then maybe think the same idea. If we were to do it horizontally, would it be the same? Would it be different? And then if we were to do it diagonally, at any kind of angle through this shape, what two-dimensional shape would result as the cross section of that figure? Once you've predicted for all of the shapes you're trying to choose, then you actually get to build the figures, right? You get to take the Play-Doh, make the 3D shape that you want, and you're going to slice it in the ways that you said, the ways that you had predicted before. Now, when you do this, again, I want to be super clear about this because this is a very common misconception that comes about, is that when we cut these pieces of Play-Doh in whatever way we decide, a lot of people think that the cross section is the whole chunk that you're holding in your hand, but it's really not. I want to be clear. The cross section of the three-dimensional figure is the face that was actually cut. It's the piece that, if you're looking at the cut itself, it's the whatever shape that is, and the whole rest of the chunk in your hand is non-existent to the cross figure. Cross figure is just the 2D shape that you're looking straight at. Okay? Now, this will be super helpful when we do this Play-Doh activity because you're going to be cutting these shapes and you're going to be looking at these faces, and it'll be a lot easier for you to determine the picture and the name of the resulting cross section.